Got it. Okay. Got it. I got a frozen window. Okay, it disappeared now. Are we live?
No, not yet.
Okay. For some reason, I cannot see Chema either.
You cannot see me?
I cannot see in the little window there.
Okay.
No.
It's all right.
Okay, now I can see you. If I switch, okay, now I can see it. I think that the issue was mine. So Rodrigo, just tell me when.
Okay, guys. I think we are live. We are live.
All right, cool. So welcome back, everybody. So we proceed with our colloquium at the National Observatory. This week, as I have seen from the messages, we have Chema Diego. It's a pleasure for me to introduce Chema here. A brief history. He finished his PhD in 2000 at the University of Cantabria, went in a mahikuhi to University of Oxford, did some tour in UPenn, MIT. Then in 2005, he got a Ramon Cajal at the Institute of Physics of Cantabria, which I assume Chema did separate institutions there.
Yes, but there is a lot of interaction between the two.
Right. Okay. And where he got a tenure as a researcher, a CISIC researcher. And 2010, 2013, that was interesting. Someday you can talk about it. He's the director of the Observatory of Astronomy of Cantabria. And about 2012, he joined JPAS. He's currently a director of the Cluster and Lensing Science Working Group. Chema has done a lot of very interesting work and many fundamental work in the area of weak and strong gravitational lensing and also CMB, and has been recently deeply involved in the JWST works, and he will tell us today some of the very exciting results that have been here in the news, and they are coming from there. So without further ado, I'm going to pass the word then to Chema.
Well, thank you, Renato. Thank you, everybody. Molto obrigado for being here. So I'm going to talk a little bit about mostly gravitational lensing with the stuff we're doing with the James Webb. Unfortunately, I cannot show much yet because most of the papers are being written as we speak, but there is something already published. But I can discuss a little bit about some of this recent work, and also even with the HST, which is very much a precursor for what we're about to do with the James Webb. So I'm assuming most of you are familiarized with the James Webb. Let me just start by saying that, as contrary to what some rumors say on the internet, this is not a star destroyer, luckily, but it's going to be a killing machine for doing science. That's for sure. So we're all very excited about it. You probably have seen this many times. It's the frequency range, or the different filters you can observe with James Webb. And I just mark one particular frequency, one particular filter, this F200, which is it's very interesting for high redshift galaxies. That's one of the benefits of gravitational lensing, is that you can see objects which are farther away. You can magnify the flux of a galaxy that is high redshift, and something that you wouldn't see normally, you can sometimes see it if it's magnified by a factor of a few. So some of the objects I'm going to present today, some of the clusters, one of the science drivers to one of the reasons why James Webb is pointing to them is to go after these very high redshift galaxies. And you can see here, for instance, that you have a galaxy redshift 15 or 16, and it's emitting strongly in Lyman alpha, for instance. So it's forming a lot of stars. You wouldn't see it below this filter of F200. You will start to see it after that filter. So it would be considered a dropout galaxy below this filter. But also, it could well happen that if you have a galaxy, a redshift 5, and it has a strong Balmer break, you may not see it also below this wavelength, and you can only see it maybe only after. So why am I saying all of this is maybe you have seen some of these claims in the literature in recent weeks about galaxies at very high redshift. This one, for instance, it was claimed to be a redshift 16. And the way it's interpreted is it's basically you're seeing the Lyman break in that filter in the 2 micron that I was pointing to earlier. Is this true? Most likely it's not. One weird thing about these galaxies is that they are extremely bright. So it doesn't make much sense that you have a galaxy at redshift 16 that is very bright. There is a famous example now, it's called the Schrodinger's galaxy, where it appears as a dropout too. You only start to see it in the F200 I was pointing to earlier. Below this wavelength, you don't see anything, and above this wavelength, you start to see the emission. So again, this is a candidate to be a Lyman dropout, and that would imply the redshift is 16 or so. But of course, if you do a careful analysis and consider other options, you can also accommodate a much lower redshift 4.6, and it's not a galaxy forming many stars, it's rather quiescent. But the fit to the spectrum is almost as good as the other one. So there's a lot of discussion going on about this. There is one clear example I cannot show yet because it hasn't been published yet, but it is clearly a galaxy at redshift 4. We know it is like that because we have a lens model for that cluster that is lensing this galaxy. And it clearly predicts it cannot be a redshift 15. A redshift 15, it wouldn't work. Such a galaxy, it would just appear in a different location than the one we observe. So it's clearly a redshift 4 point something. And the situation is very similar to what I'm showing here. It's basically a dropout below this filter. So at first, it was interpreted as being a high redshift galaxy. We had strong discussions, I would say, in the group, and finally it was, I guess everybody was on board that it couldn't be a redshift 15 galaxy, it's a redshift 4 galaxy. Very similar situation to this Schrodinger's galaxy. So there is a bunch of this. This is becoming more clear now that there is something missing with the current photo C codes. Maybe the templates are not accurate enough, and you can get biased results like this one here, where the maximum of the probability is redshift 15. Then you have a smaller peak at redshift 5 or so. So obviously you tend to believe this more, but in reality, this is the one you should believe in more. Enough of this. I'm going to jump in directly into the lensing. This is the first cluster that was observed with the JWST. If you remember, this was the image that was shown in the press release made at the White House. And for us, it was really funny to see how Joe Biden was trying to explain this image. We were concerned they would publish something before we did, but luckily they didn't. So this is the cluster SMAX 0723. I just want you to look at this number here, the archive. The data came out on Wednesday, and this paper was on the archive on Friday, which was pretty incredible. So it was the first paper, I would say it was the first paper that came out with JWST data. And the honor needs to be shared with this other paper. Just look at the archive number here in the very bottom. This is 07101, 07102. And if you want to dig into more detail, you can go to the archive and look at the time the two drafts were submitted. There is only a separation of 13 seconds between one submission and the other one, which is pretty incredible. So these two papers came simultaneously. This is ours, and this is our competitors. It was pretty crazy to get this out. Basically, we started working with a JPEG image that was published by the White House and converted that into FITS files, do the alignment and the scaling. And the first 2 days we worked with that, and then we waited for the final data to come out to do the real thing. But anyway, this is a typical image from the James Webb. Two things I would like to highlight. If you look at this zoom in the top left, you see this arc here. This is a multiple image galaxy. There's one image there. This is the second one, and the third one is right there. So this is the one that has the largest magnification, and you see all this detail, all these little clumps. There is some papers already working on this. I think a couple of them already came out, and they constrain the age, metallicity, even the size of these clumps. They are consistent with being small groups or small star-forming regions with young populations, etc. But we're seeing a lot of this now in all the James Webb images, and this is going to create new opportunities to study these small clumps where these young stars are forming. This is another giant arc there. There's two images there. The third one is this one. This is another very clear one where you see a lot of clumps as well. The third image is, where is it? It should be on this side somewhere. I don't remember. And then this one, this will come back later to this. This is interesting, but let me introduce the other papers first. Again, this is the work from the competitors, which was simultaneous with this one. What I want you to look at is the difference in results, even though the constraints are more or less the same. Like this giant arc is being used in both systems, in both papers, the same with this one. So I would say 80% of the constraints are common in both papers, but the lens models can have some significant differences, and this is only due to the way you're modeling these clusters. This is very common. Here's another interesting work that came recently from Mireia Montes. I think Renato, you have worked with Mireia, if I recall, right?
Yes, that's correct.
So this is very interesting. It's about the intracluster light, and I want you to look at some of these features here, these loops. It's completely unexpected. We didn't expect to see these things. We always thought intracluster light was a good tracer of the dark matter. We still believe that. We still think it's a good tracer of the dark matter, but we don't expect dark matter to do this kind of loopy behaviors. This is actually something we haven't published yet, but it's yet another lens model. The good thing about this model is that, contrary to what it was done in these two papers rely on parametric models, meaning you assume a halo with some ellipticity and orientation, and the halo is fully symmetric, and then you put some smaller halos around these galaxies, and then you optimize and find the combination of symmetric halos that give you the best solution, and that was done here as well. In this case, we don't do that. This is a completely free-form modeling technique, so you let the mask to go wherever it wants to go or it needs to go in order to explain the data, and you don't need to assume any symmetry or anything. It is interesting how we start to see some correlation. If you look at the blue curves, which is a model with a higher resolution than the yellow curves, you start to see some correlation with this intracluster light, and that's something very interesting that, of course, you cannot say much with only one cluster. if this pattern is true, you have to see it statistically in many clusters. But this is something we plan to do with the James Webb in greater detail that we've never done before. So this is really interesting and exciting. So this was the first cluster that was public. There is another cluster that if you want to start working with galaxy cluster data, you can go to the MAST archive and you'll find this other guide. This is another famous, well, now famous cluster. It wasn't as famous a few months ago. It's WHL 0137. And why this cluster is famous is because in the middle of this circle, there is the farthest star we've ever seen, Erandel, that I'm going to talk a little bit about it later. In fact, I'm going to talk a lot about it. But this is the actual JWST image. Contrary to what has happened, or what happened with these clusters, where you see a lot of lensing constraints, we're struggling to find new lensing constraints in this cluster. This could just be the result of cosmic variance. Maybe there is not many high-redshift galaxies aligned behind this cluster. Another possibility is that the geometry of this cluster is very round. So clusters or structures or lenses in general that are very round, they tend to produce caustic regions which are very small. So that means your chances of having a galaxy near those caustic regions where you're going to find strongly magnified galaxies are smaller as well. We still don't know that. We're suspecting that may be one of the reasons, but still needs to be confirmed. So we're working hard on producing more accurate photosys, and one of the issues we're finding is the one I mentioned earlier. Photosy codes may not be as accurate already for JWST as we were hoping. So more work is needed there in order to recalibrate those algorithms. So we found a couple new candidates here to use as lensing constraints, but they're just they're candidates. We haven't been able to confirm them. There is an observation with NIRSpec, which will get spectrum of many of these galaxies coming up in I think a month or so. So that will definitely help confirm some of these new candidates. And we'll be able to get an update on this lens model, which is going to be very, very important to interpret this little star here, Erandel, which I'm going to talk in a little bit more detail later on. So I think that's going to be, this was a little introduction on some of the clusters. There are more. We're actually working on another famous cluster, El Gordo. Some of the first papers are going to come out soon, but unfortunately I cannot share anything yet. We're finding very interesting things in the cluster. I can only anticipate that the situation is not like this. We're finding a lot of lens galaxies behind El Gordo. So that's great for the type of science we can do. But in the rest of the talk, what I want to talk is about these strongly magnified stars, like this one, Erandel, that you may have heard about it. And this is a relatively new branch of gravitational lensing, or even if you want to, you can also say a new branch of astrophysics, in the sense that you can study stars redshift beyond one individually, which a few years ago it was science fiction. If you ask me 5, maybe 6 years ago, if you could do this one day, I would be like, maybe, but I won't see it. It's not that I will see it, we're actually doing it. It's not science fiction anymore, it's reality. You can study stars one by one, only some of them, obviously, not all the stars, but you can study some stars on an individual basis up to redshift 6 so far, which is the farthest we have been able to study, and I'll talk a little bit about it. But before, I think it's very important to give a few ideas about lensing that are going to be very relevant for the remaining of the presentation. As I was saying earlier, in gravitational lensing, you normally have multiple images of the same galaxy. This one is 3 times there. you can get amplification in some of the galaxies that you are magnifying. The amplification can be large, and in some of them, in fewer of them, but in some of them, it can be extremely large. If you look at this one, this arc here, this is in reality 2 images of the same galaxy. Maybe it's better to see it here. You have one there, one there. They are kind of merging at the middle point. These two are merging also, and if you zoom in, you can actually see where they are merging. So this is the symmetry point. Like for instance, these two dots here are the same as these two. You just see them twice, but it's basically one object that you're seeing twice. And then I want you to look at these two dots here. I don't know how you see them. There is one red dot there, one red dot there, and then there is 2 blue dots there. Each one of these points is a counter image of the other one. So it's again the same object that you are seeing it twice. And the same with the blue one. These 2 blue objects are the same, but you are seeing them twice. So even without any lens model, you can know that the symmetry point goes right in between those 2 points. And these symmetry points, we call them critical curves. And the magnification of the critical curves can be extremely large. The maximum magnification is inversely proportional to the size of the object you are being magnified. So if that object is a star, you can theoretically get magnification factors of order 1,000,000. Magnification of order 1,000,000 gives you 6 times 2.5, that's 13 magnitudes. You can see something brighter by 13 magnitudes, meaning a star at recife 2 or 3, which would have magnitude 40, you can see it at magnitude 27, which is pretty incredible. So with current telescopes, you could see a star that is magnified by very, very large factors. So I mentioned magnification 1,000,000. That's theoretically possible. In practice, you can never get magnification of order 1,000,000. And the reason why you cannot get it is because this intracluster light we were talking about earlier is made of stars. And stars can do a lensing effect as well. In that particular case, we call it microlensing, and we refer to those stars as microlenses. And what microlenses do is, let's suppose this is the caustic of this cluster. The caustic is just a mapping of the critical curve, which is the region where you have this theoretically 1,000,000 factor magnification. You map it into the source plane, and it gives you a different curve, which would be normally has like a diamond shape. So if you zoom in near this region of maximum magnification, you expect something like this. As you approach this line, the magnification would go up to 1,000,000 or several million, and then it would drop to a factor 1 or 2, something like that. This is what you expect in theory, and this is what you find in textbooks, but in reality, you always have microlenses. It's unavoidable. You're always going to have stars moving around. So in reality, you never have this, you have something like this. The magnification is perturbed, and you go from something smooth, and that can reach values of order 1,000,000, to something that is more, it has like valleys and local peaks, and the maximum magnification there is not 1,000,000 anymore. It's something like 50,000, something like that. This is a zoom in of that simulation. And this is the same, I just rotated at 90 degrees. And I like this view because it gives you the impression that you are climbing a mountain, where the top of the mountain is there, and these are the peaks. And you have to think about this mountain as a transparent surface, where you can see both sides of the mountain, the side where you're climbing, and the other side, which is the one you will go down. And what these 2 sides represent are the magnification for these 2 images I was talking about. So here, for instance, you have these 2 images. So you have to think of a star, for instance, being here, and this star is in 2 magnifications. It's in the magnification from this side of the mountain, and the magnification from the other side of the mountain at the exact same position. And they don't have to be the same, they can be different, right? So you can have objects like this where one has one magnification and the other one has a completely different magnification, simply because there is one micro lens here, and there may be a different situation with the micro lenses there. Right? It's just because micro lensing introduces those fluctuations. So this is just a little intro. I want you to remember that with micro lenses, you cannot have magnification factors more than 40, 50,000, and you can have perturbations in the magnification in the two images that you expect. So again, you normally expect two images always, and one of them can have different magnification than the other. So let me review a few of the stars that we found through this technique, and we'll finish with Arandel at the end. I'll go from lower to higher redshift. The first one that was discovered was Icarus, and this was published in 2018. And before this star, we didn't even know these kind of observations were possible. We were completely lost at first when we were analyzing this data, because there was nothing in the, or basically nothing in the literature to learn about this. So we have to basically invent part of this field to interpret this observation. So what you see here, this is a famous cluster. This is one of the Hubble frontier fields. There are 6 clusters in total, very, very deep, about 400 hours total exposure with Hubble on those 6 clusters in different filters, going from the optical to the infrared. And by comparing different epochs, there was this position where all of a sudden we saw this bright point there in a position where we didn't see anything. And if you look at all the lens models that were produced for this cluster, there were a bunch of lens models, all of them very precise, because there are many constraints for this cluster. All the lens models, they put the critical curve, meaning the area where you expect maximum magnification, around that point, right? And again, we only saw one point, but we had different exposures. In a different exposure, we saw the other point. So this was Icarus in 2014. Then in 2016, we saw the other point. And then in 2017, another change in flux. So this is exactly what we expected from this situation I was arguing later, where you have a star moving in this field, it's moving in some direction, we don't know in which direction, and you are seeing the magnification from both sides. So sometimes both stars are magnified by large factors. Sometimes if you are in this area, one of them is magnified, the other one is demagnified. So it depends on when you look. You can have, I'm going the wrong direction. You can have these kind of situations where sometimes you see one, sometimes you see two, and some other times you see both, but with different fluxes. And if you look at this red curve, it goes in between these two images. So what this was confirming is that we were seeing something very magnified. The magnification here was estimated to be of the order of 1,000. So it was very magnified, and it was unresolved by HST. You couldn't resolve it. So if you take the minimum size that you can resolve with HST, which is a fraction of an arcsecond, 0.0 some arcseconds, depending on the filter, and you take into account the magnification, that means the object needs to be very small. And in fact, we found that the object had to be less than 0.5 parsecs, I believe, and it had to be as luminous as the most luminous stars we know. And there is not many candidates to explain that. The only candidate we found was actually a star. I don't have the spectrum here, but it matches really well with the spectrum of a blue giant star. What I have here is this fluctuation in flux. See how the flux is changing over the years. And this peak here, which is what we saw there in 2016, is one of those microlensing events by one of those microlenses in the intracluster light. That, as you see, there is intracluster light extending all the way up to this point. What is very interesting about these stars, you cannot only study stars that receive 1 or 1.5, like this one, you can study things like dark matter. In particular, if dark matter is made in part by things like primordial black holes, those primordial black holes will act as well as microlenses, and they will contribute to these fluctuations. So you can use the fact that you only saw one major peak in several years to set upper limits on the abundance of primordial black holes. And this game is only starting now. As the statistic improves, all these limits are going to start going down on them. Actually, this is the spectrum. I thought I didn't have it, but I do. So this is, it's not a real spectrum, it's just a photometry in different bands. But it is the first time this is known for a star beyond, our local universe. Before Icarus, the farthest star was around 200 megaparsecs or so. This, no, less than that. I think like 20 or 30 megaparsecs. I think it was in the Virgo cluster. So this extended that distance by 2 orders of magnitude. And you can start fitting SEDs to the photometry and constrain things like the temperature of the star and the luminosity. And it's incredible you can do that, aggressive one for individual stars. After Icarus, there were a few more. I'm just going to, before going into Erandel, I just want to stop in this one. This is Godzilla, and this is a very peculiar star for the reasons I'm going to explain. This is another cluster. This cluster is famous for this arc here. It's known as the sunburst arc. It's a redshift 2.37. And there is a bunch of papers about this arc alone. It has very interesting features. In particular, it's extremely luminous in the UV, and you can actually see UV that is unabsorbed all the way from redshift 2.37 up to us. So it's incredible, the ionizing power of some of the sources there. What I saw in this square is the field of view of MUSE, which is IFU machine to do spectroscopy, and you can do spectroscopy in every single pixel in this image. And that's going to be very interesting. So this is just a zoom in of this arc, this northern part. And if you look at the white circles, what you see inside the white circle is basically the same source, which is believed to be a globular cluster or star-forming region, again with a lot of ionizing photons coming out from it. It's the same source that you see up to 12 times. In this part of the arc, you see it 1, 2, 3, 4, 5, 6, 10 times. There is 2 more which are beyond this image. And so you see this 10 times, and then if you look at the white circle, there is another source which is as bright as these 10 images, but you only see it once. You don't see it anywhere else. And this has been a puzzle for years. It was proposed to be some type of supernovae originally, but this cannot be. We derive a new lens model for this cluster, and we can rule out some candidates. For instance, it cannot be a supernovae because the time delays predicted by the lens model are less than a year between the different positions where you expect to see this object, if it's a supernovae. And there are observations of this arc spanning like 7 years or so. So it doesn't make sense that you only see it in one. If it's a supernovae, you would see it in at least, you should see it in at least 3 more positions. It cannot be a globular cluster also because if you see it in one location here, a globular cluster would be bright enough to see it in other locations. So it cannot be that one. The only possible explanation is that it needs to be an object that is extremely magnified. So at this position, for some reason, you have a very large magnification, over 1,000, while in the other positions, counted images are expected, the magnification is a few tens, so you don't see them. In order for this to be detected here at this with this luminous flux, I forgot to say, but this is about magnitude 22nd, which is much brighter than Icarus and the other stars we found up to this point. So in order for this to be a star, which is what we think it is, it needs to have an absolute magnitude of -15. This is way more than the highest luminosity of any giant star we know. But it still can be a star, but a very particular type of star. Also, we can constrain the magnification, and again, since it's not resolved, that tells you something about the size. It has to be less than 0.3 parsecs. That also rules out the globular cluster interpretation. Globular clusters are typically larger than that. The other ingredient that it was missed in earlier work, we found is necessary here to explain this, is that you need a perturber. You need something that is not detected in the HST images, so something very close to that object, with a mass consistent with being a dwarf galaxy, and that introduces a perturbation in the critical curve, which is this blue curve. This is where you expect the maximum magnification. And without this perturber, the magnification there would be only, it would be less than 100, not enough to explain the flux. But if you have a white dwarf or something similar there, where the arrow points, then the critical curve does this thing. It would pass right there in front of this object. And it would also explain these two dots that remain unexplained. And these two dots, the way to interpret it is that they would be something, we don't know what, maybe another star or something like that. And you see it twice. As I was saying earlier, this is what you expect from lensing. The fact that you don't see it twice here can only be understood if the two images that you expect there has to be two images, they're so close to each other that you cannot resolve them with Hubble. So the separation must be comparable or less than the size of a pixel, 0.03 arcseconds. And if that's the case, then you will have the magnification you need, and you would produce an image that is not resolved. So that's interesting. But still, you need a magnification which is about a few orders of, you need a luminosity which is a few orders of magnitude brighter than any known giant star. Is that possible? The answer is yes. And there are stars which can momentarily, I mean by several years, not several months, like in the case of a supernovae, but for several years, they can increase the luminosity several orders of magnitude. And one such star is Eta Carinae, which in the 19th century, for about 2 decades, increases luminosity by several orders of magnitude. This is exactly what you need in order to reach the needed luminosity. But the most interesting clue, I think, is given by MUSE. If you remember, I told you there is MUSE data in all this field of view, and in particular at the position of Godzilla, it's right there. So if you look at the spectrum, you see this peculiar feature. This is known as a P Cygni profile, and this is typical in outflows, which is what you would expect in a violent eruption like what happened in Eta Carinae in the 19th century. Also, there is some Bowen fluorescent that was interpreted already in previous work, and that is also consistent with a star being in this type of phase, which is having a major outburst, which can last a few decades, or at least a few years. And then if you account for the time dilation, because this arrow is beyond 2, it would mean it would stay bright for us for at least 6 or 7 years, which is enough to explain the observations. I'm running out of time, but I want to move now into Erandel, which is the current record holder. This was the farthest star, it is still the farthest star we have been able to observe through this technique with HST, and now with JWST, there's already new data with JWST on this star. And this had a great reception in the media. It made it into a lot of media, but for me, the most interesting one was this. This is a satiric journal in Spain. It's called El Mundo Today. And basically, this came out at the same time the Oscars were happening. And if you remember the Will Smith incident, this is how they registered this discovery. Where everybody else was doing something serious, these guys did it in a really funny way. So Earandel is in this cluster I showed you earlier. It's in this giant arc. This is a galaxy redshift 6.2, and that's a photo-C redshift. We still don't have a spectrum. And again, if you zoom in this particular area, you see these two dots, which are again probably a globular cluster or a star-forming region. And this is one is a symmetric version of the other one. It's two counter images of the same object. And right there in the middle, you see only one dot, not two as you expected, but only one. Like in the other cases, we have some lens models for this cluster, different lens models with different techniques. And every single one of them puts the critical curve going right in between these two dots. And only a small fraction of an arcsecond from where this little dot is. So this is very similar to the situation with Godzilla. The only difference is that you don't need a perturber here to explain the large magnification. You already have extreme magnification that could be several thousand at this position. And it's the same story as in the other stars. If you know the magnification and you know this object is unresolved, you can get a constraint on the size. And for this particular case, and the most conservative constraint is 0.4 parsecs at most. Again, with the magnification and the redshift, you can estimate what the intrinsic luminosity must be, and even fit the photometry with some temperature, and you get a range of possibilities. And normally what you get is that the star needs to be several million times the luminosity of the sun, and with about 20,000 Kelvin, and that is consistent with a very massive star above 50 solar masses and low metallicity. So the photometry is consistent with that. This is the photometry both for the arc, where the galaxy where this star lives, and for the star, and it's consistent with what I was saying. It's consistent within one star. But now we have JWST, this actual JWST data of that very same arc. Now we see a lot more detail. In particular, these two clumps that were unresolved, they start to be resolved now. Barely, but they are not point sources anymore. They have little tails. So you can, instead of just setting an upper limit, you can actually set a lower limit. So the size of these clumps now must be 5 to 10 parsecs. Again, fully consistent with being a globular cluster. So that's probably what it is, a bunch of stars in a small region. And Earandel remains unresolved. So the resolution with the James Webb is better. The constraint on the magnification is better. So you can update the constraint on the size, and it needs to be now less than 0.02 parsecs. So you're starting to reach really, really small sizes. More interesting than that is the photometry. And this is the photometry on the left. Is the squares, sorry, the black dots. And you can see that you can kind of fit it with one star at 15,000 Kelvin, more or less. But you do a much better job if you assume two stars. So we believe Earandel is not just one star, it's two, and that makes a lot of sense, because most of these big stars, they are very rarely found alone. They normally come in pairs. And we still need a spectrum to confirm this, but the photometry now with the James Webb, it's clearly favoring this scenario more than the one star scenario alone. So we're very excited about continuing studying this object, and also these clumps. You know, there's a lot of work happening now about studying these clumps. This one too is a little unusual too, because you see it once here. If you look at, it's not very clear in this image, but if you look at some bands, you see it, somewhere there, very faint. So, but it's interesting, the fact that it's more, it's brighter there. So maybe again, you need some kind of perturber here to explain why this flux is a bit higher. It's not clear yet. Also, there is another perturber there, which is doing something funny to this counter image. We're looking at that in more detail, but that's going to take some time. So this star, Erandel, and probably this applies to the other stars too. What we believe is that this clump that we see here, this globular cluster, is probably just that, a globular cluster, and Erandel is in the outskirts. So somewhere is one of these bright stars somewhere, and you have to think of the caustic just going somewhere around this plane, and is basically getting really close to one of these bright stars, which could be Erandel. So it's magnifying that star by factors of several thousand. And this cluster, which is farther away, it would be magnified by a factor of 100 or so. And this is probably similar to the other stars that we have discussed, we are finding so far. There are other stars we found with the James Webb already. I cannot show them today. Let me just say that one of them is, we're struggling to find its interpretation because it doesn't look like any star we know in our local universe, but it could be a little bit more exotic. So we're still struggling with that one, and other ones, they seem to be more in line with what I have discussed so far. But the most exciting thing we're waiting for is going beyond this Redshift 6, which is the current record set by Erandel. And in theory, we did some estimations. If you look at this paper by Roger Winhorst, potentially we could actually see even POP3 stars at Redshift 10 or so, or 12. And that's something that when the James Webb was originally designed, I was still in the board, had been designed more than 2 decades ago. This was one of the science drivers. Then they realized this wasn't possible, and now it's possible again. It is actually possible to do that. You need a little luck, and it depends on how many POP3 stars are at Redshift 10, for instance. This is the actual upper limits of where the density of POP3 stars can be. This is for Redshift 7, but you can have up to sorry, what's this density? Up to 1,000 POP3 stars per arcsecond square in the most optimistic scenario. Most likely, we are more in this range, around 100, between 10 and 100. So what this means is, in the most pessimistic scenario, you need to observe around 30 clusters, like the ones that the James Webb is already observing, and during 10 years, and you would see one of these POP3 stars. So it's not super likely, but it is possible. Again, this is the most pessimistic scenario. You could actually start to see these POP3 stars observing 3 clusters for 10 years. And I think I'm going to finish here. I want to leave some time for questions. But let me just say one more thing, just in the last point. It's something I didn't mention earlier, but I think it's important at least to take this message home. And it is that when you have magnification factors which are extreme, and I'm talking like something of the order of 2500, which is on average of what these stars are, more or less, that is similar to having a James Webb telescope, where you have the same detector, you have everything is the same, the only thing you change the mirror, and you put, instead of a 6.5 meter mirror, you put a 300 meter diameter mirror, which is mind-blowing. It's incredible. I mean, definitely that is science fiction. We'll never have that technology, at least I won't see it. But you can mimic that telescope by looking through galaxies and looking for these very small, extremely magnified objects really, really close to the critical curves. And this is going to be very exciting in the first few years, because we're going to find a lot of this, and surely enough we'll find objects we haven't seen before. So I'm going to stop here, and if you have any questions, I'll be more than happy. And thank you again for the invitation, by the way.
Okay, thank you, Chema. It's very, very exciting. And I actually like to ask more about the things you cannot talk about, but I guess you cannot talk about. So let's open for questions. So, well, people, if you want to ask something, either interrupt or raise your hand there, please. I had a few questions. Well, I'm going to start the other way around, because I'm very interested about this monitoring. The idea to get this level of distance involves 10 years. You said minimum of 10 years with 3 clusters repeating. Yes. Okay. Yeah. So are there any current projects that have been accepted for monitoring at that level, 3 clusters? I'm assuming that to be monitoring these clusters, you'd like to get something where JWST has a easiness, like a NAP field, that you can go back there and observe it continuously for, or every year, every 6 months or something for 10 years.
Yes, so there is a project by Roger, which is right here in the bottom right, which is the PEARLS project, and we're starting again. We have 3 papers out already, or 4, and now we're getting about a paper a week out. Again, that project, for instance, we're looking at El Gordo cluster right now. We are getting data for the net within that project. The next cluster is MAX 0416, and that's the one that falls within this science case better than the other ones, because for that cluster we have 3 epochs. We're going to be looking at a cluster in 3 different epochs. One of the strategies, the best strategies to see the stars, is waiting for an extra boost given by micro lenses. So micro lenses will introduce fluctuations in the flux of these stars, and it can increase the brightness by 1 or 2 magnitudes easily. So that's that's how we found Icarus, for instance. If it wasn't for the micro lensing event, we would have missed it. But if you have micro lensing events between different epochs, it's very easy to pick up changes in flux and objects that have changed their flux. And that's one of the methods we're using to find these stars. There's another program by Patrick Kelly, is using the Hubble telescope, and that program is very clever, because he uses the widest filters available in HST, which are the clear filters, and looks at a bunch of clusters, 2 epochs, but with the same position angle, and that is critical. So you fix the position angle. So when you subtract the 2 images, you don't have to worry about any PSF distortion or anything. The subtraction is the best subtraction I ever seen, when you subtract one epoch from the other one. And we have found already 12 stars within that program, and that paper is coming out soon already. 12 stars all above redshift 0.8. And it's just a beautiful way to find these objects. They're like sitting ducks. You subtract the 2 epochs, and all of a sudden you see these sources, and they are basically flux and fluctuations due to microlensing.
Mm-hmm. Okay, so well, brings me to the second question. Can you actually separate microlensing fluctuations easily from intrinsic things like a variable star or something else?
For that, you need a good cadence, because some of these stars may be variable. So you may just find them because they are changing their flux even without a macro lens. The micro lensing light curves have a very peculiar shape, they go like the inverse of the square root of the time. So that is well known, and that's a universal law for pretty much all microlenses, while the variability could be anything else. But with just one epoch, you cannot tell if it's some of these 12 stars that we found. We just don't know if they change their flags because they're intrinsically variable, or there was a microlens going in between. You need good cadence like we had for Icarus here, right? These black dots, that was good cadence, and we had this cadence because we were monitoring this supernovae here, Grefstal. These 4 points there are one supernovae that went off, and then we predicted it would go off 1 year after there, and sure enough, it went off 1 year after there. So we were monitoring this to get the light curves for the supernovae, and that's how we saw this microlensing event there. And it fits perfectly what you expect from simulations.
Amazing, amazing. Okay, something that I thought, I'm not sure if somebody already has a project on this, but in principle, if you're looking at microlensing, this is all ICL in the cluster, in the lens. If you're going to be monitoring clusters for such a long time, can you use the fluctuation of the flux between the multiple images due to microlensing to infer the density of actually the ICL there, the real,
Yes, and we are planning to do that. We are actually working on, the way we've done this so far is by using expensive simulations of microlensing, but now we're going to switch to some kind of Bayesian analysis. We actually did that here with Icarus. We were able to rule out microlenses being more than 1-2% of the total mass, because that would produce too many peaks here. So the amount of microlensing we found here was consistent with the amount of microlensing we found by fitting the intracluster light. So you fit the intracluster light in different bands, you fit it with some SED, and that gives you a surface mass density of microlenses. And we found that something within a factor 2 of that number we got from SED fitting was very much in agreement with this lack of fluctuations in other epochs, and with the existence of a peak this bright in this epoch. But again, in order to do this better, you need better cadence. So my hope is that in the future, this will become a more standard thing. In particular, once you have a set of bright stars, and to me, the best candidate is this Godzilla because it's so bright. It's magnitude 22nd. You can actually do this from the ground. You can monitor the star from the ground. Even it's almost within reach of JPass, if JPass could see this guy. So you could monitor these objects, once a week or so for like a year. And with 1 year of observations, like 52 points, you can get a very good constraint on the amount of microlenses you have there, which some of them will come from the ICL. But if you find an excess of that, then that's the interesting thing. Could you say something about primordial black holes, for instance, with masses similar to the ones that LIGO is finding? LIGO is finding a lot of masses beyond 30 solar masses. And there is some claims that this could be primordial black holes. They would enhance this microlensing signal by quite a bit.
That's fascinating. It would be nice. This could actually normalize the surface density, normalize the amount of mass that you have in the ICL.
Right. But we're playing the game the reverse. We're getting the amount of microlenses from the ICL itself by fitting the ICL to SED. And this is something Yoli has been doing on other people. But you can actually get, it's not that hard when you have good data like this to constrain the amount of stellar mass you have there. in order to explain the ICL light. Of course, you have to make assumptions because you have projection effects. But if you do that in combination with the fact that the ICL may be correlated with the dark matter, and you get a good map of the dark matter, that's interesting. The other way we constrain the ICL is by saying, okay, the ICL must be anywhere between 0.2 and 1% of the total mass. The stars.
Right. What I was thinking is that since you're going to be having a few points, the surface mass of the ICL in a few special points, right, where you have the actual lensing, you can use this to calibrate the actual measurement of the ICL, like what I've been doing with the radially, to see if they match at which radius from whatever the center you have this particular density.
So far we're finding that for this type of events, in order for them to make sense, we need ICL in the range between 5 to 20 solar masses per parsec square. And that again is consistent with the ICL making up to 1% or 0.5% of the total mass, projected mass, which is in range with the expectations.
Okay. Great. We're a little bit late. More questions? Chairman? Well, if not, then I'll keep going. So I have a very naive question, basic, because maybe people have the same doubt. How precise, or how can you get a precision for your critical curves? Because you show some things that are quite, they look amazingly precise, and this depend, when you get the critical curves, you're depending on the model of the cluster, right?
Yeah, for instance, for this particular case of Ferrandel, you see this is one of the models and the critical curve goes right in between. I would say 80% of the constraining power comes from these 2 points, right? These 2 points you set as a constraint, the fact that they come from the same object and they are multiply lensed. One is a multiple image, one is a counter image of the other one. So when you do that, any lens model is going to try to put the critical curve right in the middle point in between the two. So you can, even without a lens model, naively, you can assume that when you have the symmetry points, the critical curve is going to go really, really close to the geometric mean between the 2 points. It's not always the case. In some cases, it gets closer to one or the other. But that's why you need more constraints. With more constraints, you can constrain that better. But for this particular case, it was very clear. All models were going.
Right. Okay. So the precision of the critical curve actually depend very local.
Yes. So this critical curve is very precise here, but it's very imprecise there, for instance.
Right. Okay.
All lens models predict different things there, but all the lens models cross there. Some with one angle, some with other, but they all cross there. So the precision is inversely proportional to the density of constraints.
Okay. All right. Fantastic. Okay. If there are, I don't know if there is anything on the YouTube. Rodrigo, can you see anything there? I can see one question here. What is this image? But this was a long time ago, so.
Yeah, I don't know what image.
Yeah, I think there's only this question on YouTube. And I don't know which image it refers.
Okay.
Yeah, I don't know.
Yeah, this was, I don't know even the time they were sent. Okay, so we passed a little bit the time. I'd like to thank again Chema for the talk. This was a very amazing, very interesting. And at the observatory, there's not many people doing lensing, actually. I don't think anybody. But this is very enlightening, and it can get the students the flavor of this field, and especially now with JWST, the jump that it has gotten. So thanks again, Chema, for taking the time.
Thank you for the invitation. And yeah. Thanks.
Thank you, Chema.
Bye. Bye-bye.
Bye-bye.